Okay, so here's a problem for us, and basically what's happening is you got this closed up box that'll hold 300 liters, and you're putting cold water in at the top and drawing warm water out at the bottom. And they give you some values and whatnot, and they're going to ask for the amount of water in the tank after a certain period. Okay, so when you begin to think about this, first question I would ask is, why is this an unsteady flow? You don't really need to classify them in order to solve the problem, but sometimes it just helps you to think about it. So pause the video and think about that. The way you can recognize that this is not steady, so it's unsteady, is the fact that this is not going to continue forever. For example, if you keep pulling water out and putting it in, unless you're putting it in at the same speed that you're doing the other one, it's going to change. It's going to fill up with nothing but cold water. So it's changing as time goes by, and that's why it's unsteady. Okay, so give some thought to how you're going to solve this. The things that we've studied in this class are mass and energy conservation so far. So give that some thought, pause the video, and think about what you're going to apply. Well, in this case, I would use mass because they're telling me a little bit about what's moving in and out, and they're asking me to calculate how much water is in the tank, so they're looking for the mass. So that's what prompts me to write the mass equation. So on the left-hand side of the black equation, you've got the mass that goes in, and then you subtract the mass that's going to come out. Now, the cold water is going to go in, and the warm water is going to come out, and that equals the final mass. I'm going to call that M2 minus the initial mass. So if you count that, there's four unknowns. There's mass 1, mass 2, mass in, and mass out. So what you need to do is think about what other things are you going to bring in that will allow you to calculate these things. You've got four unknowns, one equation, you need three more equations. So give that some thought. Oh, by the way, the reason I wrote this is mass is because what they're really looking for is M2. That's what they're looking for. Okay, so give it some thought, pause the video. Okay, so here you can see that what I'm doing is writing the relationship of the mass is equal to the velocity times the area times the density. Now, on the input, they tell me that the volume that's going in, so I'm just going to take the volume and divide by the, right here, I'm going to take the volume. Now, they put it in excuse me, in liters, so I'm going to convert it into the standard units of cubic meters. So this is the volume flow rate. Then I'm going to multiply by the time, so that'll be the amount of volume that goes in. Then I divide by the specific volume of the cold water, and that will give me the mass that goes in. This equation is the density times area times the velocity equation. So that'll be the rate at which the mass goes in. And then I multiply by time, and that'll get me the amount of mass that goes in. Now, density is equal to 1 over the volume. So that's why I just took the density and divided by the specific volume of the outflowing stuff. So now what I've got is I've got three equations, but I've picked up another unknown. The V out isn't known. So I've got 5 unknowns and 3 equations. You need something else. Give it some thought. Pause the video. Okay, so what you can see here is that I've picked up the initial value of mass because they tell me that it's completely filled with the warm water. So that means that I've got 300 liters, that's 0.3 cubic meters, and divide by the specific volume of the warm water, and I've got the mass at the beginning. So that's, you picked up another equation. So now we have 4 equations, but we have 5 unknowns. You need something else. Give it some thought. Okay, basically you don't need another equation. What you've got to do is look up the values. I know the conditions of the water leaving, the warm water that's leaving. I know it's 1 atmosphere, and it's at 45 degrees centigrade. So I should be able to find that value, the specific volume, the V of the warm water flowing out. Also, if you realize this, the warm water the water that's leaving is the warm water. So the specific volume that's going out, one of the unknowns right here, is the same thing as the velocity, the volume of the warm water. So if I just look it up, I ought to be able to get these numbers. So this guy's not really unknown. I'm going to be able to look him up. I'm also going to look up the V cold. So give it some thought as to what you're going to do, because you've got to find it in a table or somewhere. So give it some thought of what you're going to do. Okay, if you look into the tables, you'll find out that you don't really have a table for water that's at 1 atmosphere and these temperatures that are, not very high at all. Now, it is possible to find tables that have these values listed. You just don't have them in your book. What the author's expecting you to do is to use some logic to determine this. If you think about a incompressible liquid, which water is, the volume really doesn't depend too much on pressure. You have to get enormous pressures in order to change the volume at all. So basically what you can do is you can say, I will use the table for saturated water at what it doesn't matter what the pressure is, because volume isn't, it's not related to pressure. And I will look up the saturated liquid at the temperature I'm given. So for the temperature of the cold water, which was 20 degrees, I think. I'll scroll up here. 20 degrees. You look up saturated liquid at, quality of 0. It's all liquid at 20 degrees centigrade, and you'll get this volume. For the warm water is at 45 degrees. So you would look up the volume of water, saturated water at 45 degrees, and that'll get you this V here. Now, the numbers that we're going to calculate are slightly off of what the author says is the answer. The author uses for the V's, he uses 1/1000 for both. If you remember when we were doing some of the other problems, density of water was taken to be 1,000 cubic meters per kilogram. So anyway, that's what he uses, is 1,000, which is pretty close to these numbers here, but it's maybe a little bit more precise to use these. Okay, so now what you're going to do is you're going to solve the equation. So give it a try, and then pause the video and then give it a try. Okay, so here you can see what the correct answers are. M1 is 297, the area, mass out, etc. The final answer he's looking for is M2, 210. I think he comes up with 212. But anyway, that's because he uses a different density for the water. Okay, so at the last, what I'd like you to do is think about this problem. He got lucky. Well, he knew what he was doing, but it's possible that he could have given some numbers where this problem would not work out. So there's a couple of problems with this thing. So give it some thought as to what's going on. Pause it and then come back and I'll talk about it. Well, one of the problems is the fact that he says assume that the pressure is constant. But if you look at the volumes that are going in there, it's actually, the tank is actually emptying out. It's not completely full at the end of this 20 minutes. And so there's going to be a vacuum. Unless he vents the top, it's going to be a vacuum. As the water empties out, it's going to create a vacuum, and then what will happen is the pressure will go down there until you saturate the water, and it begins to turn into a vapor. So that's one of the problems, is how in the world are you going to keep the pressure constant? You'd have to have some sort of a hole there. The second thing is if he had specified a little more volume going in or a little less coming out, what would have happened is it would have filled up more. It would have had more volume going in than coming out. And since it's a closed top box, there's no place for the water to go, and it would rupture or something would change, right? So that's another issue. Fortunately, there's more volume coming out than there is going in, and so it's emptying out. The other problem is, if you notice, we had to take the density of the water going in and the density of the water coming out. And so when I did that, I assumed that all the water coming out was going to be warm water. But really, it's not. The cold water's going in at the top, and the hot water is going to rise. So it's going to want to go up. The cold water's going to come down, and it's going to mix around in there. And so the water that comes out, you really won't know what the temperature is. So you really won't be able to find the exact density. So anyway, probably doesn't matter. You learn how to calculate it, but at least you realize that there are some issues with this. Okay, that's the end of this one. I'll post it.